Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Modern life and scientific advances are both becoming ever more reliant on data. Aspects such as big data, high-performance computing, and artificial intelligence are driving a demand for robust, energy-efficient memory. New research has led to the development of a type of computer memory that has low power requirement, can be stable for years, is non-volatile, which means that it doesn't need to be continuously powered in order to store data, is high density and fast. The development involves phase change memory, where a material sandwiched between two electrodes changes between amorphous and crystalline states. Professor Eric Popp from Stanford University explains.
Phase change memory is a type of memory or data storage in which we encode the data in the change in resistance, or rather actually in the resistance of a material. Most memory structures that we're familiar with, such as those in our cell phones, laptops, and so on, typically store charge on very, very tiny capacitors. So in phase change memory, we're actually changing the structure of a small resistor. This is literally a nanoscale resistor.
To build the phase change memory, a superlattice is created by alternating layers of antimony tellurium nanoclusters with a nanocomposite known as GST-467, which is made from germanium, antimony, and tellurium. Each layer is around 2 nanometers, or just a few atoms thick, and the superlattice consists of 15 periods of these alternating layers. The unique microstructural properties of GST-467 and its high crystallization temperature facilitate both faster switching speed and improved stability. Nanoclusters serve as a precursor for crystallization and contribute to the fast switching speed of GST-467.
Some of the ideas came from our collaborators at University of Maryland. This is Haeshan Yu and Ichiro Takeuchi. So they're the ones who essentially discovered this germanium antimony telluride 467 compound. Our contribution was essentially taking that unique composition that they had discovered and putting it into our superlattices. We said, not only can we put it in a superlattice, but we can shrink the lateral dimensions of that superlattice down to 40 nanometers. Nobody had demonstrated any kind of superlattice technology with 40 nanometer lateral dimensions.
Collaborators at the Taiwan Semiconductor Manufacturing Company supplied the 40 nanometer bottom contacts to create these nanoscale devices, and the National Institute of Standards and Technology, NIST, contributed to some of the analysis of the structure. Remarkably, these tiny devices simultaneously exhibit low resistance drift, good endurance, and fast switching. First author Shanzhen Wu from Stanford University explains the significance.
It's been long known in this memory technology that there is a trade-off between the thermal stability and the speed that you're able to operate the memory device. It's sort of what nature gives us, right? There's no free lunch for most material combinations. But in our technology, we're able to sort of break this trade-off, or even push this trade-off to the better corner with the combination of superlattice and the nanocomposite.
The superlattice enables efficient switching. To effect a phase change in the material, and hence change the resistance, a pulse of current is passed through the material. This causes localized heating, and the heat is confined by the layers of the superlattice. The superlattice is also vital for minimizing low resistance drift, which is where there is a gradual change of the resistance states over time.
So we have been working on the superlattice for a while, like the last 5-6 years, or maybe even beyond that. But this work has reached the peak of any of our previous work, in a sense that having a low power memory technology is great. Having a faster memory technology is great. Having a memory technology that can switch millions of times is great. But if you really want to have them together in one memory device and want to see the best of all these worlds, not like one world, two worlds, many different worlds, and want to combine into one world that has the best possible scenario, it is really challenging. We still cannot say that this is the ideal case, but at least this work shows the peak of all those metrics dumped into one cell. After all these years of development, based on our prior knowledge work, we are able to get to a point where we really see all these things coming along together still in one device.
That was Dr. Asir Khan, visiting postdoctoral scholar at Stanford University. Zhang explained some of the challenges the group overcame to arrive at this remarkable breakthrough.
Individual layers are only 5 atoms thick for the antimony telluride, right? So how to controllably deposit all these layers without them intermixed or like growing into each other, that's one of the challenges we overcame. So we did a lot of material optimizations, like the growth temperature, how which the sputtering power going to optimize the material layering, and also what is the growth pressure. So these are some of the challenges that we overcame.
We've demonstrated operation below 1 volt. Getting any kind of memory to work at 1 volt or below is good news. The reason is that modern computer processors all operate about 1 volt or less. And many types of memory don't work well at 1 volt. Exactly how the resistance changes is a function of voltage. And you can see that there's some major changes happening below 1 volt. And these are repeatable and reversible. So that's one thing. The other thing that I wanted to mention, we essentially show 8 resistance states, which are completely distinguishable. They're essentially storing 3 bits of data in the same physical memory cell. That's a much higher density than can be done with other technologies. The important part here is that the resistance states are distinct and they are stable with respect to time.
So, the research has led to a device that is smaller than anything created so far. It involves a new way of combining materials, shows improvements in trade-offs between speed and stability, operates at low voltage, and shows promise for high-density, multi-level data storage. The research shows how fundamental material science can interface with circuit and system engineering to eventually create a new product.
So it's a very exciting time because we're actually seeing this potentially scale up into systems. And I think once there's academic demonstrations that this can be scaled into systems and it's really worth doing it for things like artificial intelligence applications, our main job is to essentially show the technology value to the world, and then maybe convince companies that it's sufficiently interesting to pursue. Where we sit, we see both sort of like the really fun materials questions, but I think we also sit in a place where because we interact with computer scientists and with industry, we sort of see their needs and what they need to make this work.
Some of these industries are looking for phase change materials that can withstand its state for years, even at an elevated temperature like 150 degrees Celsius. In this work, we showed that, we have their GST467, but there are, of course, other combination of materials within their stack. And by tweaking the other material layer in that stack, for example, to name titanium telluride, we can engineer or tweak the retention temperature. So we can use some of those thermally stable material within the stack that might help the technology to be operated even at, I think we showed up to 130 degrees C. The ultimate goal for the industry is to go at 150 degrees C. So there must be some other magic material combination.
This work was published in a recent issue of Nature Communications. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at mrsbulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.